I have the pleasure of introducing our keynote speaker for this year's Alumni Day festivities, Professor David Charbonneau, PhD 01. The title of his work is The Terrestrial Worlds of Other Stars. So allow me to introduce Professor Charbonneau. First of all, David Charbonneau, as I mentioned, is one of us. He earned his PhD in astronomy in 2001 right here at Harvard. He is the Fred Kavli Professor of Astrophysics at Harvard University. He enjoys working with students and postdoctoral fellows to develop novel methods and instruments for the detection and characterization of planets orbiting other stars. And he studies how the life cycles of the parent stars affect the presence and properties of the atmospheres of any attendant worlds. Professor Charbonneau is a member of the National Academy of Sciences and the American Academy of Arts and Sciences. He recently co-chaired the congressionally commissioned study outlining our national strategy for exoplanet research, including the search for life on planets orbiting other stars. In recognition of his contributions to the development of the field of exoplanets, Professor Charbonneau was awarded the Kavli Prize in Astrophysics at a ceremony in Oslo in September 2004. Friends, please welcome Professor David Charbonneau.
Yeah. All right, good morning. How's everybody doing? Good? Yeah. All right. Ready for some astronomy? You know, we're going to do some astronomy here. Okay, good. Yeah, I mean, maybe while the screen comes down, I'll just, reflect, because this is a gathering of, Harvard PhDs. I mean, the greatest professional opportunity for me ever was to be admitted. I remember the moment I was admitted to the astronomy PhD program. And I arrived and I was super eager to do research, and I thought I was going to work on something completely different. And the first planet orbiting out of the star had just been discovered. That happened just a few months before. I was at the University of Toronto as an undergraduate, never heard about it. Arrived, everybody was talking about it, and somebody stepped forward and said, I'll advise you on a project on this. And I said, oh great, are you an expert? And he said, no, I don't know anything about it. But the interesting part is that nobody does, because it's a brand new field. And that's what I walked into as a PhD student here in 1996. And professionally, that just radically transformed the path I was on. I'm not going to talk about that history. It's a really, not my personal history, but just the history of exoplanets. That's not what I'm doing today. I want to tell you about what we're doing this year in exoplanets, because it's so exciting, okay? But I'm happy to talk about that in questions and kind of the whole history of how central Harvard was and Harvard Astronomy and the PhD program in a lot of these developments. Okay, so what I want to do for about 45 minutes is just really talk to you about terrestrial exoplanets. Okay, so we're talking about planets orbiting other stars, but not any old planet. Okay, so we're talking about these planets. You recognize, so that's the Earth. Okay, then we've got Mercury, Venus, and Mars, all drawn to their correct scale. Okay, and so terrestrial planets mean planets that are made of iron cores with rocky mantles, and they might not have an atmosphere. Okay, Mercury has no atmosphere. They might have an incredibly thick atmosphere like Venus, much thicker than our own atmosphere, or a very tenuous one like Mars. Okay, and so the kind of the questions that are really exciting to me is how do these terrestrial exoplanets, these Earth analogs, how do they get their atmospheres? Why do some of them lose their atmospheres? And really what's driving that is this big question of, can we figure out if there are other planets orbiting other nearby stars that have life on them right now, okay? And that was a crazy fictional thing to work on when I arrived in graduate school, and now that is something that we're very much focused on as a nation, as in terms of funding, big projects in astronomy, and something that our students really now are working on in the Department of Astronomy. Okay. Okay, so how are we going to go and look for life in the universe? So I'm going to present some different potential paths. So here's one idea. Okay, so I'm a big science fiction. Are there any other science fiction fan? Yes, come on. Who isn't, right? Who isn't? There's those that admit it, and there's those that don't admit it. But all right, so here's one idea. Okay, so this is from the movie Interstellar. And the idea is we're going to send spaceships. We're going to figure out how to find, how to build spacecraft and launch them towards other stars, and we'll just directly go and interact with life on those planets. Okay, so if we took the fastest macroscopic thing that we've ever built, okay, which are some of the missions that we've launched in the solar system, and we pointed them directly at the closest star to us, that would take 100,000 years to get there. So we do not know, and you know, there are ideas about how to do this, but we are nowhere near building that kind of machine, okay? So I don't think that that's a viable path, okay? All right. Okay, so here's another idea about looking for life in the universe, okay? Recognize, who's this actress? Good. And this is from the movie Contact, right? And so in Contact, she is a, extremely, I would say, sort of altruistic, young PhD student. She's got a mean advisor who's trying to steal all the credit all the time. Anybody had that? Okay, so, and then, but because she is pure of heart, okay, she basically figures out a way. The book, by the way, if you ever get a chance, read the book Contact by Carl Sagan. In the book, she's a much more interesting character because she's not a perfect person in the book. In the movie, she's kind of a simple person. Okay, or a simple character. So here the idea is we're going to go and we're going to listen for aliens that are trying to communicate with us by sending radio signals or laser signals. Okay, so that's also really interesting. We've done it. We've sent signals to other stars. I mean, not me, but humans. The trouble is, I think there you're looking for a very specific kind of life, right? You're looking for life that's technologically advanced, life that is really interested in radio telescopes, and life that wants to communicate. And so what I think when we do, this idea is called SETI, the Search for Extraterrestrial Intelligence. And I think when we engage in that, we're really looking for copies of ourselves. And I think that that's a very interesting idea. We gaze out at the stars and we're asking, can we find a mirror image of ourselves? Because we do those things. We love technology and we are very interested in trying to communicate with aliens. Okay, but maybe, whales don't seem to be interested in that. Okay, there's lots of forms of life that don't engage in that. And so I think this is a too narrow of a net. You see what I'm saying? It's not a great first step. So instead, this is the idea. Okay, so if you were an alien and you were looking at the terrestrial planets of our solar system, there's something really different about the third one from the sun. Okay, the continents are green as opposed to brown. Okay, it's not subtle. Like from far away, the Earth looks different, and it's different in a very specific way in that the second most important constituent in our atmosphere is oxygen, and that oxygen is made entirely by life. Okay, if you extinguished all life on the Earth, the oxygen would disappear within hundreds of thousands of years. It would rust. The exposed iron would react with the oxygen to make rust. Okay, so we're constantly filling our atmosphere with oxygen because of photosynthetic activity of plants. And there's other molecules in our atmosphere that are also produced only by life. So the really interesting idea is, can we find planets orbiting other stars, establish that they are rocky like the Earth, and then look for things like molecular oxygen that we can uniquely attribute to biological activity? That is something we can do now, or at least in the next 5 or 10 years. Okay, all right. So that's the idea, okay? All right. Okay, so how are we going to do that? So we're gonna do it through this method of transits. Okay, so the idea is you might think, just build a telescope. You take a nice picture. There's a star and there's a planet next to the star. The trouble is that planet is 10 billion times fainter than the star, and they're very close together from our point of view. So we don't have that ability yet. The light from the planet is lost in the glare of the star, okay? So instead, we're gonna use the star to our advantage. And the idea is when the planet goes in front of the star is now a flashlight. It's backlighting the planet. And we study the light that passes through the planet's atmosphere. And we do spectroscopy. We analyze the colors of light. And then we look for the specific molecular fingerprints that point to different atoms and molecules. And that doesn't require this incredible imaging technology. Okay? All right. Okay. So we need a big telescope to do that because we need to gather a lot of light from the star. And we now have some very big telescopes at our disposal. So a few years ago, NASA launched the James Webb Space Telescope. This is the most powerful optical infrared observatory ever launched into space. It is transformative in many, many fields, particularly for this beloved field of exoplanets. Then the other, even bigger telescope on the ground is called the Giant Magellan Telescope. This does not exist yet, okay? And that's a collaboration between universities, including Harvard, and we hope the National Science Foundation, and it's currently under construction in Chile, okay? Yeah, that's right. Well, I'm happy to talk about that in the questions, okay? But, you know, the idea here, this is truly enormous, okay? So this entire mirror here is smaller than one of these mirrors, okay? Okay? And then there's, you know, so this is, you know, I'm 2 meters tall. I'm about this big, okay? So this is a truly enormous observatory in Chile. And we need that to gather enough light, okay? But the point is we are building that and we do have this facility. And so the question is, can the James Webb Space Telescope and the Giant Magellan Telescope, can we use them to detect molecules like oxygen, water, various, methane, CO2, and really learn about the conditions on distant exoplanets? Okay, so the answer is yes. Okay, mathematically, you calculate, do I get enough photons in enough time while the planet's in front of the star so that I could, you have to, but the answer is yes, you can do it, but not for all stars, okay? Obviously, if a star is in another galaxy, it's too faint, okay? So the stars have to be close, okay? So close for me is 50 light years, okay? Okay, so that's really, really small, what's a good analogy? So if I shrank the galaxy to the size of the United States, our Milky Way galaxy is the size of the United States, this would be, like the size of Central Park in New York, okay? So we're talking about just our closest neighbors. You get that? So I shrink it down, and we're just talking about very, very small, but there's plenty of stars in that volume of space. That's okay. Okay, and the stars have to be small. Okay, so you can kind of see how that works. I'm trying to study this this blue annulus. That's the atmosphere, and it's more advantageous to me if I can shrink the star, because then the blue annulus is a bigger fractional area of the star. You see? So I want the star to be small, and I want it to be close to me. And then, yes, it works out. Okay. So, of course, we don't know yet whether there are such planets around those stars or whether those stars, I'm going to tell you all about that, but that's kind of the experimental design. Yes. Okay. All right. So, now, a bit of astronomy. Stars come in all shapes and sizes. Okay. We orbit a star called that. We assign letters to these stars to tell us about their sizes and temperatures. And that entire scheme of letters, that was all invented at Harvard 130 years ago by a group of women who were the Harvard computers. And that's a very fascinating story about how they made major advances in terms of understanding what stars were made of, just up the road at the Harvard College Observatory. And here we are, we've inherited that nomenclature, okay, 130 years later. Okay, so sun-like stars are called G-type stars, and I've drawn the sun to scale, the big one, with the Earth to scale. Okay, you see how hard that would be? But then it turns out that the galaxy makes all sorts of stars, And there are these much smaller stars, which we call red dwarfs, or if you want to be an astronomer, you call them M dwarfs, because they're the M spectral type. Okay, but the main thing to understand is that they're physically smaller, typically 20 or 30% the diameter and the mass of the sun. Okay, all right. It turns out that these stars are far more numerous than sun-like stars. So when I was in high school, I was told a lie. I was told many lies, but I was told one of the lies I was told was the sun is an average star. Okay, the sun is not an average star. The sun is much, much bigger and much more luminous than most stars in the galaxy. The most common kind of star in the galaxy is like this guy. Okay, so these guys outnumber sun-like stars 12 to 1. Okay, so for every sun-like star, you've got 12 of these guys. So there's plenty of them. The Milky Way and nature loves making these red dwarfs. Okay, so now I'm going to chop it down to the ones that are small enough that if we can find a planet that goes in front of them, then we can use the observatories we have to study the atmosphere. Okay, all right. Okay, so what I'm going to also do is tell you about some of the really amazing young scientists that I've worked with just in the last few years on these ideas. I'm going to be showing you. So this is the first character in our story. This is Jen Winters. And Jen basically defined this sample of stars. And I said, Jen, how many, can we go find all the stars in that volume? So picture a bubble around the sun, which goes out to 50 light years. That's our, so we're basically saying in Central Park, how many trees are there? So now we're saying in this volume of space, how many stars are there? And she had to do a lot of work. And the answer is we know about every single one, there's 413 of them. And so that's the sample we're going to study. Okay? All right. And so the questions we're going to ask are, how common are these terrestrial worlds? What's their rate of occurrence? Okay. Do any of those stars actually make planets? I don't know. Maybe they don't. How common are Jupiter-like planets, big gas planets, which are easier to find but have a big impact on, the Earth was very influenced, and I'll tell you about that, about the existence of Jupiter and Saturn. And then also we need to understand the stars. Okay. So the conditions of the Earth are very much set by what the sun does and the energy that the sun gives to us. And so we need to understand what these red dwarfs are doing in terms of their energy as a function of time. Okay, so those are the science goals. And then I build telescopes. What I really do is I build telescopes, I design telescopes, I build telescopes, I work with students to use this observatories. So I got to tell you about the hardware because this is all the fun stuff. Okay, this is not theory. Theory is, I'm sort of reading my way through all the Sherlock Holmes short stories right now. And there's so many great quotes in there about the primacy of data. And he says it is a capital offense to theorize without data. You must first observe, and then you can begin to form ideas about what you're seeing. But first, just go out with an open heart and observe, okay? And astronomers, we are observers, okay? Okay, so there's 3 projects I'm going to describe. One is called the MERTH project, one is called the TESS mission, and the other is some ground-based astronomy, okay? All right, so this is the MERTH project. We are looking for Earth-like planets around what kind of star? M stars. We call it MERTH because it makes us happy. Okay. So, and the idea is we have 8 robotic telescopes in Arizona at Mount Hopkins. It's about an hour south of Tucson. If any of you hail from there, just north of Nogales, on the Mexican border. And then we have 8 telescopes in Chile because, of course, we want to see all the stars. And you can only see some of them from the southern hemisphere and only some from the northern hemisphere. Okay, so you have to have 2 facilities. And it's entirely robotic. So every night, this facility wakes up and it has this list of 413 stars. And these telescopes are looking at each one in turn. So basically, we look at a star and we measure its brightness. And we're trying to see a planet run in front of that star. Now, the stars are all over the sky. So we look at one star and then we look at another star and another star. But we have to come back to any one star every 20 minutes because the planet takes about an hour or 2 to go in front. And you don't want to miss it. You don't want the planet to wait and you observe and then it runs in front. You don't want to miss that, right? So you have to go back every 20 minutes. So this is what it looks like and there we are in the north and the south, okay? but this is what it looks like in practice when we're getting data. So this telescope here is looking at many stars. Up top, I'm showing the brightness of one of the stars, which was a completely random star until about 20 minutes from now. And all of a sudden it notices that the star's brightness is lower than it was previously. And this telescope, in real time, without any human interaction, stops what it's doing. It says, I really care about this star now, because I think there's a planet in front of that star. The planet then, if it is a planet, passes out front of the star from our point of view, and the telescope goes back to its regular observing, okay? And so, okay, so you're saying this is the low cadence data. We're doing this like every 30 minutes, okay? This is hours. So 1 hour, 30 minutes later, 20 minutes later. It noticed it has this green data where it's doing a probability calculation, saying that's weird. It's weird that it's faint. Now, is it faint? Oh yeah, it's really fainter. And then it turns to blue and it says, I'm gonna stare at this thing until it goes back and notices that these data are now at the same level of these data and says, okay, fine. They'll figure it out in the morning when they wake up. I'm gonna go back to my regular cadence of just observing stars, okay? And this is that is it. That's the discovery of a rocky planet orbiting another star, okay? And so then we can go back and really study that planet. Artist conception, okay? What we actually know over here, okay? But you know, this is actually the cover from that congressional. Basically, Congress had asked us to do this national strategy. Like, what are the opportunities that you mentioned? That's the cover from that National Academies report. Okay, you can tell it's not the Earth because there's all these other planets. So here is the passage of the planet in front of the star. Okay, we're measuring the brightness of the star. The star gets a little tiny bit fainter, like 0.5%, okay? And then this is a separate measurement where basically we're measuring the wobble of the star. The star and the planet orbit each other, and we can measure the change in the speed of the star. That tells us the mass of the star. Okay, so we get the mass of the star here. We get the size. We have a sphere. If you have a sphere, and you know its diameter and you know its mass, you can figure out its density. You calculate the density, it's the density of the Earth. You're cooking with gas. Off you go, okay? So and we do this and we found a bunch of these, okay? Now, they have terrible names, okay? So my wife's name is Margaret, and if you run into Margaret, they're all named Margaret, okay? But among astronomers, they have terrible names because they're named catalog names after the stars. So just to warn you, you're gonna see some of those names in a second, because the stars have names and the stars are simply like numbers, and then we associate the planet with that. But we do give them nicknames, okay? So for example, this planet, initially we thought had a lot of water on it, so it was a water world. So we named it Kevin as a nickname. Does anybody get that connection? Because you saw the movie Waterworld, Kevin Costner? Yes, okay. All right, okay. All right, so then the other facility, so that's from the ground, and then I'm also part of this project called the TESS mission, okay? So the TESS mission is to try to do that, but from space. So space is great because, you know, we don't have to, the sun doesn't come up into our field of view. The weather is always good in space, okay? So space, but it's much more expensive. And so for perspective, like our telescopes in space, the telescopes on the ground were 40 centimeters. The MERTH project, each of the telescopes is about that big, okay? Here, the telescopes are about 10 centimeters, so they're literally that big, okay? Because, launching heavy things into space is what makes it very expensive, okay? All right, so, here's the mission to scale, so you can kind of get a sense, okay? So this is not a big space. I'm happy to talk about like how this all gets paid for and so on, but physically this is not a big object, okay? This is sort of human-sized, okay? And it launched in 2018, went down to Cape Canaveral with my 4 daughters to see this, and it was really, you work on this for many years, and there's this sort of 1 or 2 minutes of terror where you put this thing that you put all this love into and you put it on a giant rocket, okay? And you're like, oh God, I hope that thing does not blow up. And it didn't, okay? So we got into a great orbit. I thought it was kind of fun to show you how it observes, okay? So this is artist's conception of how it observes. So there's 4 cameras, and the cameras are pointed like this. So at any one moment, when you point at the sky, you're measuring a strip on the sky. Okay, that's one of our cameras, okay, which has a large field of view, okay, and we study stars. But at any one moment, we have 4 of these cameras, okay? So I take the telescope and I point this way, and I'm getting basically the strip of stars, and I study that set of stars for a period of time, and then I have to map out the whole sky. So then I move on to the next set of stars. So I look for, maybe 28 days in one direction, and so on and so on. So I do 13 of these around the sky, and then I flip over, and the next year I do those 13 sectors. Okay, and then we can go back and do this. So now we've been extended because the mission is very successful. So we've been remapping parts of the sky. And then you can find longer period planets that you didn't have enough data to find before, but you can basically find a lot of planets this way. Okay, so the combination of the ground-based telescopes and tests allow us to really find the planets we're looking for. Okay, so did we find any? Did we find any? Yes, we found one. So, okay, many of them. Then the other element of this is spectroscopy, okay? So the other 2 projects measure the brightness of stars, and they tell us about the sizes of the planets, because it tells you the star gets fainter by a certain amount, so how much of the area of the star were you blocking? But we also want to know the mass of the planets, and so we have to go and basically measure the Doppler shift of the star, okay? And the star, if it changes in velocity, because it's do-si-doing with the planet. So picture it as like 2 dance partners, but one of them is much bigger than the other one. But the big partner still is dancing around with this unseen planet, okay? And it's coming towards you and going away from you and towards you. And that's this wobble that we're measuring with these spectrographs. But this is great like you can imagine, the students are going out to Arizona, they're getting these data. These are facilities that we run in collaboration with our colleagues at the Smithsonian. Okay, so the Department of Astronomy is very special at Harvard because we're embedded in the Harvard Smithsonian Center for Astrophysics. And this is the same Smithsonian that runs all the museums that I hope you've visited on the Mall in DC. And I love the Air and Space Museum. You might have your favorites. I love the Air and Space Museum. Same group of people have research facilities, and their research group of astrophysicists are partners with us. And we collaborate to advise students. So it's a very wonderful relationship. Just across from the old Radcliffe Quad. Just go up Garden Street, okay? All right. Okay, so those are the projects. I just wanted to kind of show you like the facilities. Now we're going to talk about what we actually found. Okay, so did we actually find any planets? Okay, so I want to introduce this guy, Christo Ment. Finished his PhD in 2023. He's now he's a postdoc fellow at Penn State, okay? And I want to show you some of the work Christo did. So, here's an example of a discovery of a planet. And you can see there's this kind of wave, this vast ocean of variability, okay? So he's looking at one particular star, and the star is rumbling and getting brighter and fainter, and then on another night he gets these data, and on this night he gets these data, and it goes up and down. And on that giant ocean, which is caused by spots on the star, and the star is rotating, and the star has flares, on that ocean of variability, there's this tiny little boat that's passing in front of the star at regular intervals. And that's the planet. And then he has this mathematical model that explains both, and he can say, yes, we really did find a planet. Okay, but just to show you, like, this is hard, it's very subtle. I mean, it's like, there's no concern that these aren't real, because then we go get subsequent data that's unambiguous. But the initial detection is a very interesting challenge dealing with a very complicated data set. And this is an example. This is AI. So AI, he definitely was very interested in applying machine learning and AI to accomplish some of these tasks. Okay, and so it was very interesting. Like he was taking a course in the computer science department about machine learning and AI, and then for a final project, they said I can actually use my own data for my project. I said, let's try that on some of our Mirth data, and he was able to find planets using AI, because the machine learning aspect is really good at like characterizing data, okay? So it wasn't just like he had to write a whole algorithm, but he used the idea of machine learning to get at it. Okay, so, all right. Okay, so these are the planets that we found, okay? And these are various members of the group and a few other groups. just to show you what those data typically look like. And as I said, they all have uninspired names, but you're welcome to call them what you want. Okay?
David, the development office wants to know whether there's a naming opportunity.
Oh. So you are totally allowed to name a star whatever you like. There is no restrictions on that. So absolutely, the trick is that you cannot own the star's name. So other people can also name the star. Okay, so there you go. Okay, now the one more technical. It's really, if you go to a 45-minute science talk and there's no data, be suspicious. I'm going to show you some data. Okay, so because I want you to really feel there's no magic here. It's just a very we have an idea, we build a telescope, we get the data, and then we do some statistics. Okay, so there's no mystery here. I mean, the planets are mysterious, but I don't want there to be any confusion about how the conclusions are coming from the data. Okay, so then working with this guy Christo, what I'm going to show here, okay, is I'm going to show a plot. This is the planet radius in Earth radius. Okay, so that's the size of the Earth right there. Planet's a little bit bigger than the Earth, like Venus is here. Okay, like Mars is here. Okay, so they're all there. And then this is called insolation. So you're like, oh, that's weird. So insolation, you understand, okay? But this is the effect of the sun, which we call sol. So this is insolation, okay? And the idea is how much light is the planet receiving relative to how much the Earth receives. So, a planet here gets 200 times as much light per unit area, per unit time, like every second, the amount of energy heating the surface of the planet compared to the Earth. But then we go all the way down to planets that are not getting much more than the Earth. Okay? So for all of our planets that we've discovered, we know those numbers because we measured their size and we've measured their distance, and we know how luminous the star is, so we know how much energy they're getting. Okay? And so here are the 7 planets that I showed you. These 7 planets, I'm going to plot them here. Okay, 1, 2, 3, 4, 5, 6, 7. Okay? And then I'm going to plot these curves, and those curves are the sensitivity that we would have to such planets. So you can imagine that bigger planets that are closer to their stars, we find those easily. Okay, so if I go down, planets that are twice the size of the Earth, basically have 100% sensitivity. And then if I make the planet really small, like if the planet has, 10% the size of the Earth, I can't find those guys. Okay, I just don't have the quality of the data. But the point is, I'm in this realm where, sure enough, I'm finding planets that I'm sensitive to. But what's really interesting is, here I have 100% sensitivity. How many planets did I find here? Right, I found no planets here. Okay, so right away, you can say, oh, why are there, if nature made planets of all sizes, why didn't I find them there? And I didn't find them. And similarly, you can say, here, here I have 70% sensitivity, and I have 1, 2, 3, 4, 5, 6 planets kind of right there. You go down just a little bit to 50% sensitivity, and I'd expect to find 5 or 4, but not 0, but I found none. So right away, what you can see is that there's a preferred size for terrestrial planets. Yes? So if nature made all these planets, but we don't. We see that planets preferentially, not uniformly, but preferentially are the size of the Earth. Okay, so whatever process made the Earth and Venus, it seems to be universal. We assume that's gravity and chemistry. Okay, it's physics. It's making Earth-sized planets around other stars, very different stars than the Earth. Okay, so the takeaway is that for these small stars, very different guys than the sun, there's at least one rocky planet for every 2 stars. We think there's more, and that's because we still are looking at planets that are quite close to their star. There's more, you can go down to planets that are farther from their stars, and we just couldn't do that in this experiment yet. We're doing that now. But already we know there's at least one for every 2 stars. And the typical size of the planet is the size of the Earth. Okay, fascinating, great. Now, what about Jupiter-like planets? Okay, in the same systems, like if I have a rocky planet, do I also have Jupiter-like planets for these stars? Okay, so I'm going to show you some images from the solar system. I'm going to ask, what is this object? What is this object? It is not the moon. What is it? It's Mercury. But everybody says the moon because it looks the same as the moon. Mercury and the moon are not geologically active and they have no atmosphere. So they were both totally bombarded by asteroids, things from the outer solar system during some phase in the past. So if you look in the distant past of the solar system, there was clearly a moment where all this material was raining down on the planets. It happened to the Earth as well, but the Earth has erased that information because the Earth is geologically active. So we have volcanoes, we have plate tectonics, we have oceans. You can see a little bit on Mars, right? Mars has an atmosphere and we think had liquid water, but you can still see some craters. But then for these guys, okay, and this really is the moon and that is Mars, you can see there's this enormous period of bombardment. And we call that the late heavy bombardment because it happened long after the formation, the initial formation of the planets. Okay, but it was an epoch. Okay, what caused this? Okay, what caused this was Jupiter. So Jupiter and Saturn, when they formed, they migrated, they formed and they moved around. And there was all that, like, think of the solar system as you've just built a series of buildings and there's all these leftover like cinder blocks that didn't get used. Those cinder blocks, those are the asteroids. That's what asteroids are, okay? And also things that are farther out in the solar system where the cinder blocks are not really rock and iron, but they're mostly water. Jupiter and Saturn migrated, okay? So I'm showing, here's Jupiter and Saturn as a function of their distance from the sun. And as they moved around, they gravitationally took all those cinder blocks and they fired them in towards the inner planets. And that's epoch was basically defining for the Earth and Venus and Mars because it set the surface composition of the planets, okay? So we think there are theories that a lot of our ocean was material that was far out in the solar system that was deposited on the Earth through the gravity of Jupiter and Saturn. So why does that matter? Well, it means maybe whether or not you have an ocean depends on whether you have a Jupiter-like planet, okay? Or certainly the composition of the atmosphere, those volatiles, that's going to be set by whether this happened in other solar systems. So it's really important to know whether this population of terrestrial planets we have are accompanied by Jupiters, okay? In the solar system, we know there are other sun-like stars, we know they are. What about these low-mass stars? All right, so that question fell to Emily Pass. She just finished her PhD last summer. She's now a prize fellow at MIT. She's a postdoc fellow. And so Emily did this really extensive study using all that spectroscopy I talked about, the wobble data. Okay, and she looked at all of those stars, the 413 stars, and she wanted to find how many times did I find a Jupiter, and so did most of the systems that have rocky planets, do they also have Jupiter-like planets? And she looked at all those stars, and she found zero, nada, okay? So these stars are really good at making rocky planets, just like the sun is, but for whatever reason, they do not make Jupiters. And so when we think about these planets, it's easy to sort of jump and say, these are analogs of the Earth and Venus. They're siblings. They're just around more accessible stars. But maybe they're not. Maybe they're more like handshaking third cousins, okay? They're made of the same stuff, but they grew up in a very different ecosystem, and their composition, particularly their surface composition, is radically different because of the absence of these other Jovian planets, okay? All right, then this last important part is trying to understand the lifetime over which the stars are magnetically active. So what do I mean by that? So I mean when the solar system was formed, the sun was spinning quickly and it had enormous amounts of X-ray emission. So it fired X-ray and UV photons at the Earth, which would have totally blasted away our atmosphere, totally irradiated all life on the planet, would have killed all life on the planet. The sun is now very calm. The sun has slowed down, it's calmed down, it's not magnetically active, it doesn't do this anymore. But we know it did it in the past. However, it did it only for the first 100 million years, and the Earth's atmosphere was produced through volcanic activity after that. So there was a period where the Earth was just getting hit by X-rays all the time, The sun stopped doing that, and then the Earth made its atmosphere. And that sequence is important because the Earth can keep its atmosphere if it didn't have to go through this moment of X-ray irradiation. Did that also happen for these M dwarfs? Okay, so that's the idea. The very active star is gonna really start to bombard the planets, and can the planets hold on to their atmosphere, or are they gonna lose their atmosphere? Okay, and we we think that's why Mercury has no atmosphere, because its surface gravity is weak and it's really close to the sun. So it lost that battle. We lose some of our atmosphere all the time. The atmosphere is escaping the Earth right now, but it's being replenished by some volcanic activity. So we're in balance. Mars has very tenuous atmosphere. It's mostly lost that battle. Obviously, you need an atmosphere for life, we think. Life as we know it. Okay. Okay, so I want to show this picture of Amber Medina. She was a PhD in 2021. I really like this. She was a great thesis, talking about jobs outside of academia. Amber now works at the White Sands Air Force Base because she grew up in Las Cruces and she wanted to work in Las Cruces. And I love talking to Amber because I said, Amber, tell me what you're working on now. And she said, David, I can never tell you what I work on because I have a top secret security clearance. I can't even bring my phone into the facility. Don't ask me what I work on. Okay, but I also love this photo because it was very touching. This was, I don't remember, we had this moment, the pandemic, and she had to defend her thesis. She had gone home to Las Cruces and was completing her thesis in her parents' house and had to defend over Zoom. Okay, we couldn't have an in-person defense at the time. Then we quickly did after that. But after she was successful, she emerged from her room, and what her parents had done was bought her the Harvard robes, and she put them on, and then they had a giant party, which I watched over Zoom. And, and then the local newspaper found out about this and they went and took her photo. And this photo is actually from the Las Cruces newspaper. So I really like that photo. And then of course Amber and other graduates from my group then came back, and then we had an in-person ceremony for these students that were caught in that 2020 and 2021 year. So it was a really very happy story in the end, okay? And Amber's like, great, doing great. Okay, I wanna show you her work here. So here is data from the TESS mission, remember the space mission, and we're measuring the brightness of stars over time. And so this is time in days, okay? So here's, 1 day goes by, 2 days go by, another day. So this is sort of 10 days of data. And if you look at the data, you see this perfect wiggle, 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 wiggle. What's causing that? So the star has spots, and the star is rotating. And the spots, when they're in view, the star looks a little fainter because the spots are darker, and the spots go out of view and it gets brighter. So the sinusoid, this wiggle in the star's brightness, that tells you how quickly the star is spinning. Okay, and that's the key to understanding if it has X-ray emission. But the direct evidence that this star has a lot of incredible activity are these things. You don't see them in the negative, you just see these positive excursions here. So she subtracts this from the data, and now you can really see these guys. Those are flares. Those are giant events on the star where material is launched into space, okay? Any one of those flares is far more energetic than anything humans have ever experienced. Okay, so if those flares are launched from the star and they strike planets, they would do an incredible amount of the removal of the atmosphere, okay? So like in the 19th century, there was one of the strongest flare the Earth has ever experienced. It's called the Carrington event, okay? They didn't know what it was at the time, but all telegraph wires were destroyed, okay? It was totally annihilated because it overloaded the electromagnetic impulse just annihilated all these telegraph wires. We now know that that was a solar flare. So we do worry about, like in terms of the practical stuff that NASA does, like we do get 8.5 minutes warning when these things happen. And there are things you can do to your electrical systems to shield yourselves. And these rare events do happen from the sun, but they don't happen every day, which is what's happening here. Okay, so I want to show some work from Elizabeth Newton, who did her PhD in 2016. She's now a professor at Dartmouth. And what she had done was to take all of our data and to measure how quickly the stars spin. Okay, this is just the mass of the star. Remember, we're talking about stars that are sort of 10 to 30% the size of the sun. And she noticed that the stars fall into two groups. So this was a big discovery. People didn't know this. She found that there's a whole bunch of stars that spin, so sorry, 10 to the 0, 1, okay? 10 to the 0 is 1. I don't know why we plot it this way. So these stars spin once every day, 1 day, a tenth of a day, so 2.5 hours, okay, 10 days. And then there's nothing in the middle. And then there's these stars that seem to spin really slowly, like every 100 days. So the sun spins every 25 days. So these stars seem to fall in these two groups. And we now understand that this is an evolutionary sequence. Stars start spinning rapidly and they then spin down. But the key part is these are the ones that are capable of destroying atmospheres. And these are the kind of chill older parents that just let their kids do what they want to do and don't get in their face. Okay, so, all right. So now just to show you how that works. So basically we know that stars are born at a constant rate in the galaxy. And so if you look at a volume of the galaxy, you count up all the stars, okay? And those stars, for that stars, I know they've been born at a continuous rate over the last 8 billion years. And I observed that half of them are active, spinning quickly, and half of them are spinning slowly. Then the moment at which they spin down should be something like 4 billion years. Does that make sense? They're being born continuously, and I have equal numbers, so therefore I conclude they're spinning down at 4 billion years. And what she found, and this was work with Emily Pass, finding that the fraction converts into when they spin down, and they spin down between 4 billion years, or 1 billion years. But in all cases, it's much, much, much longer. The sun spun down in 50 million years or 100 million years. Now these stars are taking 20 times longer to spin down. So the planets produce their atmospheres through volcanism, but the star is still active, and we worry that the star is stripping the atmospheres of these planets. Okay? So, and this is all, just to be clear, this is all discoveries and things happening really in the last 18 months. Okay, like Elizabeth data, that's from 2016. That's the oldest data I've showed you. But most of these conclusions are just coming out month to month now. So it's very rapidly moving field. Okay, so to end, right, so what do we actually know? Do any of these terrestrial worlds that we've discovered, do they actually have atmospheres or not? We worry that they don't because we've now learned about their stars. Okay? Okay, so this is work from Dr. Laura Kreidberg. Laura is now a director of the Max Planck Institute. So it's an extremely senior position in Heidelberg. Laura had this really great idea. Basically, she used an infrared space telescope, okay? And as the planet goes around the star, okay, the planet is tidally locked, okay? That means it always presents the same face to the star. So what that means is at times you're looking at the night side of the planet, and at times you're looking at a half illuminated planet, and sometimes you're looking at the day side of the planet. Okay, if the planet has no atmosphere, then the day side should be really hot because it's getting all the energy and it's re-radiating it, and the night side should be really cold. So that's the case for Mercury. So if you look at the dark side of Mercury, it's basically ice cold. If instead the planet has an atmosphere, then that effect is basically muted, because the atmosphere redistributes energy across the planet, okay? So when the sun sets tonight, it's not gonna be 0 Kelvin, I hope. The temperature's gonna go down a little bit, but very small compared to absolute 0. Okay, space is almost at absolute 0. So the point is, you get basically the day side and the night side are the same temperature and therefore the same infrared brightness if you have an atmosphere. So she picked one of these planets that was one of the most accessible ones. And here's the day side emission, and here's the night side emission, which basically goes to 0. So you conclude there was no atmosphere, because she can see that the night side is ice cold. And basically the atmosphere can't avoid, it's compelled to redistribute the energy. If you heat a bunch of gas and you have cold gas over here, you must have this flow of gas. It's just basic physics, okay? So this idea now is widely used, and so and this is really like this. Some of the stuff is just the last week. These are the planets that have been studied by this method so far, okay? And we're gonna work our way down. They're easy to study if they're hot, because you don't have to look as long, you get more data, you get lots of infrared emission, okay? So we're working our way down in temperature, okay? And by we, I mean, this is an international effort. So do these planets, these particular planets, do they actually have, so here's a really hot one, did that study, nope, no atmosphere. Here's the one that Laura Kreidberg had done, so I already told you no atmosphere. Here's one of the Earth planets, oh, no atmosphere. Okay, we're gonna go down to these other planets, no. And then this most recent one, maybe. Okay, so in that case, the day-night contrast is actually not stark. Currently with the James Webb Space Telescope, we're looking at a bunch of planets that are even colder, farther from the stars, and thus I think we're gonna find what we call the cosmic shoreline, the point at which they have retained their atmosphere. So like this, I'm not saying all of these planets don't have atmospheres. These are basically the Mercuries, and this confirms our theory, right? But we do believe there's a temperature at which the planet is cold enough to hold on to its atmosphere, and we will see that in the coming 6 to 12 months. Okay? Okay, so, all right, so the big kind of takeaway, what are you talking about with family? Okay, so these are the big takeaways, okay? So terrestrial planets of these, so low mass stars, but basically the most common kind of star, they're extremely common, so at least one for every 2 stars, but they grew up in a system with no Jupiters. They experienced extremely high levels of X-ray and stellar flares for billions of years, which is much longer than how long that went on in the solar system. And a handful of the hottest planets have lost their atmospheres, and I don't mean that's a theory, I mean we've measured that. JWST, this James Webb Space Telescope, should soon tell us whether the cooler ones have suffered the same fate or not. Okay? All right, so I hope I gave you a picture not just of the science, but kind of the people involved in the science. And also I really wanted to connect the actual facilities that we build to conclusions that we make about the physical universe. So I'd be thrilled to answer any questions you have. That's my talk. All right, any questions? Okay, well, I see a bunch of hands, so I'll leave it to the folks with the microphones to handle that. Okay. All right, so we'll start here. Yeah.
All right, how close are we to being able to actually resolve optically, as opposed to, looking at the differences in intensities?
Yes, so you mean actually take a picture?
Right, can we actually see, for example, the diameter of a star?
Oh, yeah, great question. Okay, so we are now able to see the actual physical extent of stars through a process called interferometry. So we have multiple telescopes that are widely separated, and that gives us a very precise angular resolution. So you can actually see the star is a circle and not just a point of light. In terms of being able to do the other thing, the kind of more straightforward thing, so yes, there's these 2 important paths. That was the conclusion of this report that we produced for the National Academies. This is the opportunity now for low mass stars. But we must also study stars that are like the sun, because we know that at least in one case, those stars made planets with life on them, okay? So it'd be foolish not to simultaneously develop a path to study sun-like stars. This method doesn't work for sun-like stars because they're too big, so the whole transit thing falls apart. So in that case, we have to build a facility that has incredible angular resolution. And basically the decision made through the National Academy, the recommendation through the National Academy is basically through a consensus-based process where we get input from people all over the world, is that we're gonna build this thing. It's called the Habitable Worlds Observatory. That is the next big flagship for NASA. So think of like the Hubble Space Telescope, this James Webb Space Telescope, those are flagship missions. The next big one that we should start development on is called the Habitable Worlds Observatory. So that is exactly, so it will do exactly what you're thinking. It will take images of stars and planets, directly allow us to do spectroscopy for planets orbiting stars that are identical to the sun. Yeah, but that is new technology development. We don't know how to do that. So a big part of NASA missions is you do all this tech development. It's like the opposite of what works in industry. Like in industry, if you figure out something really good, you make 1 million of them and you sell them, right? What we do in astronomy all the time is we do all this technology work and we build one. We build one special tool, unlike anything that's ever been built, and we launch it into space. It's kind of a strange field to work in, but we have a vision for what it is, but we have to work out now the technology. NASA's really good at doing that in partnership with universities that have incredible students through the support of the national government. So that is the way we get these things done. Yeah. Okay, I see lots of other hands, so whomever.
So I compliment you on this wonderful presentation. I learned so much.
Thank you.
You didn't spend much time on the other half, the key variable, which is on volcanism.
Yeah.
Could you give us a little education about that and why you were confident that this only happens at a certain window, which is the thing that determines the conclusion? Thank you.
Oh, that's a great great question. So that is mostly, those ideas are mostly based on studies of the solar system. So the solar system is our ground truth when we have ideas about planets around other stars. So we can establish, when did the Earth build up a significant atmosphere throughout its lifetime? And we can see that the Earth relatively quickly built up an atmosphere, and that's through signatures in the geology, in the oldest rocks that we can find. We can also see that the Earth's amount of oxygen has changed a lot, right? So the Earth had a long period of time with no oxygen. It also had a period of time where oxygen was higher than the current amount, and we can see evidence that there were very large fires, because when you get to a certain amount of oxygen, things become flammable, right, spontaneously. So it's through studies of the Earth and also through studies of Mars and Venus that we sort of figure out that time scale. It's also more fundamentally just based on the kind of the basic physics. Like if I make a planet, the planet starts off hot and cools over time because it loses heat to space. And it's when it's hot is when all the gases that are trapped in the rocks, okay, like carbon dioxide, those are going to be cooked out, those are going to be degassed at the highest temperatures. So we also have a more fundamental idea to think that's just something that would happen early rather than later. If you look at, Mercury now, Mercury is completely solidified. There's no molten core in Mercury. So Mercury has no volcanism. But the Earth still has active volcanism. Venus, we're not sure. Mars, largely not. And that's consistent with our picture that the biggest planets took the longest to cool down. So the Earth is still cooling. Mars and Mercury, are already cool. Yeah. Moon is an extreme example. That's completely ice cold. So, yeah. I'm going to let her decide. Okay.
I have 3 questions.
Yeah.
So the first is among the stars that you have selected, how many of them have transit planes that are observed?
Oh, yeah. Right. So a big correction. So of course, the orientation of the planet's orbit cares nothing about where we are. Or it'd be spooky if they were all aligned with us. That would be interesting. But that's a simple geometric correction. So basically, it depends on the distance of the planet from the star. As the planet gets farther from the star, there's a smaller range of angles where this thing is still in front of my hand. If I move it in close, there's a bigger range of angles. Okay? But typically think like 1 in 20 of all the systems out there happen to be aligned so that their orbital plane is in our line of sight.
And is the...
So we find those 7, but you should inflate that number by 20. Right. And that's how you reach the conclusion that half of stars have at least one of those kinds of planets.
Is the method for measuring the heat of the bodies by Laura Kriegberg, is that dependent on whether or not a planet makes a transit?
Not entirely. So basically, we find the planets by transits, and those are the ones we study.
Right.
But if you had a system that was face-on, okay, so you always observe this as like a half moon would be the situation, there'd be no signal, right? As it goes around, it isn't modulated. But if it's intermediate, okay, where you sort of see a mostly dark planet, a mostly illuminated planet, yes, you could still use that to see those faint signals due to planets. But you wouldn't directly know the diameter of the planet because it doesn't go in front of the star, and that's how we get the diameter of the planet.
I see.
Yeah.
And then the last question is, given the stars that you've measured being of lower mass than the sun, to what extent does that affect the hypothesis that a Jupiter-like planet is necessary in order to draw parts of a building universe to make the Terran planets? If there isn't the right mass balance between the star and another body,
Yeah.
then can you expect some fraction of that universe to just fly off course and not form Terran-like planets?
That's right. We think that the planets that you get around a given star are really dictated by the protoplanetary. So when you make the star,
Right.
sort of 1% of the material is left over in a plane, and that's what goes and makes the planets.
Right.
And this goes back, the first person to propose that was Kant, right? So Kant noticed that all the planets were in the same plane and rotated in the same direction that they orbit, and said, oh, they must have all formed out of a disk. So those ideas are really interesting. Go way back before there was this, before philosophy and natural sciences separated, right?
Have you?
So the idea is you're really dictated by the mass of that disk. And yes, we think these low mass stars have lower mass disks, and that's why they don't make the Jovians. That's our explanation for it.
Sure.
And you certainly could have a situation where there's almost no disk and you don't get any planets.
But are you looking for a Jovian that's scaled to the sun or that star of that system? It's going to be smaller, right?
Well, it still has to be massive like a Jovian to have the gravitational influence. So that's right. So I didn't show you the actual, that's right. So Emily's study clearly ruled out like Saturn mass and Jupiter mass planets. It could be that really all you do there is form Neptunes, and there she doesn't have quite the sensitivity, but she still didn't find any, and she still can say that. So for the Jupiter-like planets, we could say less than 1% is the actual statement of those stars, because you never say 0, because you could have just been unlucky.
Sure.
But less than 1%. For the Neptunes, it's more like less than 10%, but it's still a pretty good constraint.
So, I mean, my question really is are you screening by ratios of suns to Jovian?
No. I mean, we're studying all stars
I see.
in this volume of space. We don't leave any out.
Okay, cool. That's all. Thank you so much.
Yeah, my pleasure. Okay, there's a question here. Oh, okay, we're gonna go here and then maybe here. Okay.
A fascinating talk, beautiful storytelling. And of course, I immediately become suspicious when the story is so clean and linear.
Well, you should read my papers.
And so I guess there are two related questions that this brings up, which is how confident are you in the story as a whole, and are there elements of it where if you pull them out, things will collapse? And the other is what paths along the way failed, basically? What hypotheses failed and
Oh yeah, sure.
didn't lead to a beautiful story?
So there's a lot to unpack there. Yes, it's a strange thing when you are the first to discover something when you're first to see a phenomenon. Even if it's a phenomenon you're looking for, I was the first person, as a graduate student, I was the first person to measure a planetary transit ever. Okay, it was a big planet, but that's what kicked off this whole, okay. And my first reaction wasn't, oh, great, that's the thing I'm looking for. It's this fear, it's this like, is it real? Is the data messed up? And if the data are correct, is the planet interpretation the only valid interpretation? So this is definitely, I worry. I stay up late because I'm an astronomer, but I do have sleepless nights even when we're not getting data, thinking about, is there another explanation? So there are observable facts, like I can see there's a star that gets fainter every few days, and those are sort of unimpeachable because, other groups are very eager to verify or disprove what this Harvard guy says. And so lots of people have gone and done their own observations, and they see the same phenomenon. So that's a powerful method in science, where we basically have an audience that is not adversarial, but critical, and want to measure things for themselves, and they do so. So I'm not really worried about the observational data. When you get to interpretation, like my story about the atmospheres and when that's happening and so on, then that leads to other experiments. So then you think, okay, now I want to actually measure things that distinguish between alternate interpretations. But a theory that is not tested by observations I don't give that much weight. Okay. I don't know if I quite answered your question. What was but I think there's a difference between, observational facts and then the physical theory that underlies them. Sorry, and then the second part was?
Well, you told a very compelling linear story.
Yeah. Well, I was basically wanted to tell you the experiment we've been doing for the past few years. So, yeah.
But if you read in the history of science, usually things go wrong in certain places, or there's a misinterpretation which lasts a few years until someone comes along and says, "Oh, actually, this is this thing."
Yeah.
Have you just been very lucky or very smart or whatever? Had any problems like that?
I mean, there are definitely many claims in exoplanets that I felt at the time were not well established by the data, and they fell apart over time because of the scrutiny of other researchers. Okay, so definitely, I try to really set a very high bar for the statistical significance before we go out and make claims, and that's sort of above the community standard. And I think things that are in that gray zone, the danger, right, is if you sort of think like, well, if I do an experiment and I see what we might call a 3 sigma event, that means I have a distribution of potential outcomes and I see this real outlier. But you don't factor in the fact that, you've done this experiment 100 times, or other people have done this experiment, and now you're pulling out the one time you saw something interesting. So we're very thoughtful about that. We do try to avoid that. So certainly I've seen things in the data that initially got me excited, but we didn't publish, and then we got more data, and we didn't see the phenomenon again. So I do think we're just trying to be very careful about that. Yes, I think that in terms of understanding these planets, we may learn. I mean, it really, one competing hypothesis for those planets. So okay, let me give you an example. When you measure the density of a sphere, okay, and you infer a composition, that's based on saying, the density of iron is the same as the density of the planet, and therefore the planet's made of iron. Okay, well, that's kind of a big leap. Maybe the planet is made of another element that has the same density as iron. But in astronomy, there's a bunch of elements that are very, very abundant because supernovae make them, and there's a whole bunch of elements that are very rare. And so you're folding in in a set of observations about stars generally that they're just as predominantly iron. But that's an example where there could be something perverse. And there is an explanation of some of these planets, which is that water is a big fraction of their, so you could change it so I have, instead of having iron and rock, I could have a smaller amount of iron and rock, boost the iron, but then add some water on top, and I get to the same density. And that leads to another experiment. Can I study something that tells me there's water in the atmosphere or not? So that's a current debate in the field as to whether some of them, I think they're terrestrial planets, but I think there's another explanation that's plausible. It's more complicated, but it's still plausible in that they're water worlds. So there's a lot of, so I've tried to avoid most of those debates in this talk, but I mean, definitely, this field now, like there's 800 people at the meetings, and mostly there's real debates. It's a rapidly moving field. Yes.
One thing that worries me a bit about this argument is the arguments over the age of the Earth, maybe around 1900 or so.
Okay,
And,
yes.
Right, Lord Kelvin said the Earth can only be 100 million years old or something because of the energy balance.
Right.
But then radioactivity was identified
Yes, right.
as a huge component there.
Yeah.
And then the development of complex life involves a bunch of special atoms that are heavier, that are only created in supernovae.
Right.
And the age of the Earth is only 4 billion years or something like that. And so the Earth's materials have been recycled multiple times over the age of the universe. Now, are you seeing, with these red dwarf things, are you seeing maybe things which could never support life because they haven't been exposed to these heavy elements?
Oh, yeah, great question. Yeah.
So,
Yeah.
not to say that there aren't Earth-like planets out there, certainly we hope that there are, but there's this other constraint on the development of life.
Right, that's right. No, it's great. I get it. So one of the most profound observations in planetary science is that if you look at the sun and you count up through spectroscopy, you take a spectrum of the sun and you say the sun has this much iron and this much magnesium and this much silicon and this much oxygen. And then I said, let's imagine that I make a planet and I lose all the hydrogen and helium because those are light gases and they're not bound. The Earth has the identical relative ratios of those elements. So if you look at the Earth, the amount of iron to magnesium to silicon to oxygen is identical as we see in the sun. And so that's one of the main arguments that we think planets are formed in a disk out of the same stuff that made the sun. It's just that the planets didn't hold on to the hydrogen and helium. So it's profound. So when we look at other stars, we can do spectroscopy of the stars and we can see the elements in the star. And so that's why we're comfortable saying we think the planets are largely made of those same elements. So that's the chain of reasoning. Okay, now about life, unlike many of my colleagues, I'm quite agnostic about whether there is life. You know, people talk about, is there life elsewhere in the universe? And I think that because we now know the universe is infinite, that's a very interesting question. But I'm an observer, I'm a scientist. And so for me, the question is not whether there's life that I have no access to ever through any conceivable telescope. That's not a scientific question. The question is there life in the volume of space that I can study with the instruments I have? And that's a much more narrow question. So now we're talking about hundreds of stars. And so life could be a phenomenon that is quite rare. Maybe it's unique to the Earth, or maybe it's just 1 in a million. But I could definitely go and study all of these planets. I talked about the slightly hotter ones, but there are ones that are in what we call the habitable zone. And it wouldn't surprise me at all if we find out that there's no life on them. Yes.
Well, these Earth planets that you're finding, are these there near these red dwarf planets?
Yes.
Are they going to go along and blow up and then destroy these planets?
Who's gonna? What do you mean?
What's the lifetime of the star?
That's a great question. So stars, the lower the mass of the star, the longer it lives, which is a little counterintuitive because stars live through burning their hydrogen, nuclear fusion of their hydrogen. But the way you have to think about it is the massive stars are like rock stars, and they're just burning through life at an incredible rate, and we love them, but they're gone by 27, right? And that's because the density of their cores is so high, the fusion rate is so high, and that's why they're so luminous. M dwarfs, the sun we think will ultimately live 9 billion years. We're sort of halfway through that. These M dwarfs can live hundreds of billions of years. So they're not under threat of that. Yeah, and there's so many interesting things. We know of M dwarfs that we now know are actually much older than the Earth. And so we're looking at terrestrial planets, but the planets are not 4.5 billion years old. The planets are 10 billion years old. And that's also fascinating because it is a window into the processes, the physical processes. I'm not talking about civilizations and things, but just the physical processes that the Earth is the Earth is constantly evolving. And it's a way to think about, here's some real data on what happens to terrestrial planets in the next 5 billion years. Yeah. Yeah. Yes. My pleasure.
Okay, we have time for one final question.
Thank you. You didn't address, you said you would talk about this later in question, the political context of the present. And we often think of Harvard as a private university, but much of what you do is in this kind of public-private partnership, to put it mildly.
Yes.
So what is the outlook over in the current conditions for the work you and others are doing?
I mean, I'm an immigrant here. I'm from Canada. Okay, it's not that far, but I was an F1 visa holder walking the streets of Cambridge and Somerville. Okay, so I really value that one of the greatest strengths of the United States, okay, is research universities, the contribution of research universities to applied science, okay, to cancer research, to development of COVID vaccines, and also to fundamental science, okay, the discovery of the age of the universe, the discovery of the size of the universe. And that demands federal funding because normally the federal government both is the largest financial partner. Okay, there are no private foundations that can match what the federal government could do. And also normally is enormous force for stability. Okay, private foundations can be fickle in terms of what their immediate objectives are. Not necessarily, but some are. Normally, if you've heard about gravitational waves, the discovery of gravitational waves, the NSF invested in that for 30 years before they found a single signal. And then they broke through, and now we find them every day. And it's a way to learn about the distant universe through a kind of radiation that is unrelated to light. It is a totally different kind of radiation. It's called gravitational waves. And the NSF was a stable partner for 30 years in that. And so I think the positive way to say that is that if we want, as a nation, if we want, we can be the ones to find out if there is life in the universe, if there's aliens out there. The actual question the actual answer to the question that everybody on Earth asks themselves when they're 5 years old, okay, are we alone? We can do that together. Harvard and other private universities in partnership with the federal government. And I hope, and I think we should pick that up, and that'll be one of the great things we do as a nation. And I truly believe that.